Good afternoon, students. Today I am going to tell you about zero order reaction. I was telling you about chemical kinetics. I have told you about the average speed, instantaneous speed, and today I am going to tell you about the zero order reaction. And in this zero order reaction, I will be telling you about a bit intro about it. What are the zero order reactions? I will tell you about the integrated rate law, about the half-life time of a zero order reaction, and about the graphs which we encounter in a zero order reaction, and about some of the examples of zero order reaction. So let's start with what a zero order reaction is. So as we all know, let's consider a very simple case, A forming products. And if we formulate the rate of reaction, then for a zero order reaction, the rate will be, I am writing it directly, rate will be equal to K and raised to the concentration of the power will be 0. Since we are considering it a zero order reaction, and as you all know that this is the formula for the rate of equation, and this is the rate constant, which is the specific rate constant or the velocity constant, multiplied by this is the concentration term for A and raised to the power 0. I have written it 0 because we are considering the zero order reaction. So this means that the rate, it does not depend on the concentration, because anything raised to the power 0 is 1. So this will come out to be K. If we solve it, it will come out to be K. This means that the rate for a zero order reaction is equal to the specific rate of the reaction, and it does not depend on the concentration. Moreover, the rate of reaction will not depend on the time also over here. So if we plot a graph for a zero order reaction between rate and the concentration, then since the rate remains constant with concentration, then this exercise is our concentration, this is our rate, then what we get is a single straight line. Means that the rate remains constant with concentration. The concentration will change with time. Okay, the concentration will change with time, but the rate will not change with the concentration. Moreover, another graph that can be predicted for this is, suppose this is our rate abscissa and this is our time abscissa. Then the rate will remain constant with time. And these are two peculiar things about the zero order reaction. Okay, so zero order reaction is one in which the rate of the reaction, it does not depend on the concentration, and the rate law can be written in this way, and rate is equal to the rate constant. Okay. Now let's come over to the integrated rate law. Now I will tell you about the integrated rate equation for a zero order reaction. तो अभी मैंने एक सिंपल सा रिएक्शन लिया है A फॉर्मिंग प्रोडक्ट्स. तो अगर इसके रेट ऑफ इक्वेशन की बात करें तो क्या होगा, रेट इज इक्वल टू K is the our specific rate constant multiplied by this concentration term of A raised to the power 0. I have taken it 0 because it is a zero order reaction. Okay. जैसे कि मैंने पहले बताया था कि रेट इक्वेशन अगर लिखनी है किसी रिएक्शन की, तो हम लोग स्टोइकियोमेट्री को कंसिडरेशन में लेते हैं. उसी तरीके से यहाँ पर अगर हम रेट लें तो क्या हो जाएगा, माइनस dA by dt minus 1 by 1. It is 1, so 1 by 1 dA upon dt. Okay, so we can write the rate in this form also. We can write the rate in this form also. Minus I have put here because A is getting consumed. Okay, so this is also our rate equation and this is also our rate equation. Both are so same, so we can equate them. We can equate the equation number 1 and equation number 2. Let it be equation number 1, let it be equation number 2. And since both express the rate equation, so we can equate them. What we get is minus dA upon dt is equal to A raised to the power 0. And since anything raised to the power 0 will be equal to 1. So what we get here is that this will be 1 and what is remaining is only K. So what we get is minus dA upon dt is equal to K. A slight of rearrangement over here, dt we have shifted to this side and negative side also to this side, just for the sake of simplicity, because when we are going to solve something, we have to make rearrangements in it. So dA will be equal to minus K. Now let us integrate this equation. to solve this d factor, and we have to integrate it now. So let's consider when time is 0, means initially. When time is 0, then the concentration will be how much? A naught. Then it will be the initial concentration I have taken in this book, A naught. This is the initial concentration. And at any instant of time t, this concentration of A will be how much? A. Let it be final concentration. Final concentration. And when we integrate it between the limits of A naught to A, is from initial to final, and the temperature from 0 to T, what we get is A, limits A and A0 and A, and similarly here we get K is a constant, it will come out of the bracket, and we have time with limits of from 0 to T. So when we solve it, it is very simple calculus. What is A minus A0 will be equal to minus A T minus 0. So this comes out to be A minus A naught is equal to minus A T. 0 we have removed, it will be minus K. A slight rearrangement over here, and what we get is A is equal to A naught minus A. This equation is known as the integrated rate law equation, because we have derived it from the integrated rate law. So it is known as the integrated rate equation. Okay. So you have got this. Should I repeat it? Okay. So this is our integrated rate equation for a zero order reaction. The final concentration is equal to initial concentration minus K, the rate constant, and T is our at any time T. Okay, at any time T when we are taking, then this final concentration will be equal to initial concentration. A0 is initial concentration, and here is the rate constant, and T is our any time T at which we are doing the experiment. So I will explain one thing more over here. If we observe it, what we find is that it is actually the equation for a straight line. What we do is A is equal to minus Kt plus A naught. I have made a bit rearrangement, and if we notice it, it is actually equation for a straight line. Y is equal to mx plus c, where c corresponds to A naught, x is for time, and y axis is A. This means if we plot y and x, then we will get a straight line, the slope of which is m, and the intercept on the y axis is c. So if we compare these two equations, okay, if we compare these two equations and we plot a graph between y and x, means between this concentration A and time, okay, x corresponds to time and y corresponds to concentration, means if we plot a graph between concentration A and this x-axis time, this is our time axis. On x-axis, if we plot a graph between two, then we will get a straight line, the slope of which is given by n, and here the n is minus of k. Minus k is the slope of this curve, and the slope is given by, this is our theta. So slope is given by tan of theta. So tan theta will be equal to minus of k. Okay. So this is our concentration term, and this is our time axis. And if we plot a graph, we will get a slope. We can see that the slope is negative and corresponding to minus of k. This is slope minus of k, and the intercept on the y-axis, which is c, on the y-axis is given by A naught. So this will give us A naught. This is our initial concentration, and this is the straight line which we get the slope, and the slope is also given by tan of theta, given by minus of k over here. So this was all about the integrated rate law equation, and I have told you about the graph also. And after this I will tell you about the half lifetime. Half lifetime means the time taken for the completion of half of the